Okay. Yeah. So hello everybody. I'm Neil Krishnaswamy, and I'm going to be telling you about a new um, type system slash verification system that I and Christopher Polta and actually I won't say all their names because it's like a huge host of collaborators. So what we've been working on is we've been building a new type system slash verification system for C. And you know, what would the idea here is that we're trying to build a verification system for verifying like low-level systems code, and the focus of our effort is actually not on type correct programs, but on type incorrect programs. So we want to design a system that's sort of good enough that we can give it to an adventurous kernel developer, and they will be not incredibly put off by the experience. Um, and so what's going on here is, so what we're reporting on is all work in progress. So I'm telling you a lot about aspirations and things that we've done. There's probably about 60% of what I'm going to tell you. And so because it's C, we need to track memory management, and we need to track memory. And so this language has substructural types. And because we actually care about like the actual behavior of the program, we've attached that to an SMT-based refinement system, so that we can say things like the length of an array and indices are in bounds, and that like you know the functions clearing pages are actually clearing pages, and things like this. And so you can ask, okay, well, why are you doing this? Like, shouldn't you be doing something like, dependent type theory or something? And the reason is that Linux comes with this hypervisor called KVM, and KVM is a number of years old, and it's used widely. But quite recently, KVM has grown a bit. So Google has built an extension to KVM called pKVM, and standing for protected KVM, and it's an extension for Linux ARM that's intended to run underneath Android. So the next generation security infrastructure for Android is allegedly supposed to compartmentalize the OS and use the hypervisor as a way of isolating different security domains from each other. And because this is like sort of going to run on a billion devices and be security critical, it's going to be a really important target for verification. And in addition to being important for verification, it's plausible that we can actually do it, because the whole thing is only about 8 or 10,000 lines of C compiling to C in assembly, compiling to about 14,000 machine instructions or so in the most recent version. And so this is tantalizingly possible to verify. And so we want to verify this, and by we, I mean not just the people on the listed in the authors, but also collaborators at multiple universities. We want to verify pKVM, but then our second goal is we would like to move on to other things and do other research. And we don't want the proof to bit rot. And so one of the research goals is we want to produce some kind of verification artifact that the kernel developers can go on to maintain, and we can go on to do other research. So the fact that we want a Linux kernel developer team to use it imposes certain constraints on us. So it's not really reasonable for us to ask them to radically alter their workflow. So we can't ask them to learn an entirely new program logic that you run in a separate proof assistant, entirely separate from their existing editors and IDEs and compilers, because that would just be too disruptive for them to adopt. And so this led to the idea that, well, maybe what we can do is add fancy types to C. And then, programmers are used to dealing with type errors, and we know how to put them into IDEs, and maybe that will fit nicely into it. And this puts us in a certain amount of a design tension. So we want fancy types to express rich properties, but because we want non-type theorists to use this system, we need like a very predictable, reliable behavior. So we can't run tactics that might work or might run forever. We can't do the heuristic sorts of things that automated verification people do with the sort of best effort thing. We need to be able to say yes or no every single time, and when we say no, we need clear, understandable type errors. So that's like sort of the design aesthetic of cyanide. And as I should note, like I said before, this is all sort of in progress. So we haven't completely achieved all of these yet, but like we're pushing towards it. And so here's a little example of a cyanide annotated C. And so this is a function called clear page, and it receives a pointer to a page of memory, so 4 kilobytes of memory, and its job is to zero it out. And so you take your C program as it is, and then we add some annotations to it. And the annotations include things like preconditions. So here's a precondition saying that the range of memory from 2 to 2 plus 4096 is a valid range of memory. And we have post conditions saying something like, look, all these points from like 2 to 2 plus 4k, they're going to be 0 at the end of the routine. And also, because this is C and every variable inside is mutable, we have a second post condition saying, oh yes, and we didn't modify your argument on you. And this program works the way that you expect. It starts at 2 and then iterates byte by byte, zeroing it out. And so we need to add some loop invariants saying, okay, when you're halfway through the loop, half of the loop is going to be 0 and the other half is going to be whatever bytes you started with. And one additional thing to note here is, okay, so we also have to add some additional annotations to manage these predicate definitions. So CN's substructural annotations are a bit like separation logic with things like points to assertions, and we can build abstractions on top of them, like the byte and 0 byte abstractions. And when we have these predicate abstractions, the programmer actually has to say when to pack and unfold and fold these definitions. Possibly it could be automated, but there's a philosophical point that we want the behavior of the type system to be like quite predictable, so that when the user gets an error, they'll be able to understand it. And speaking of errors, let's take a look at what a cyanide error looks like. So here on this snippet of code, we have S2, which is a struct with a field X, and we have a function G, which is going to dereference X and then increment it. And it looks perfectly innocuous. We say inner arrow X and then we increment it, but cyanide complains. And why does it complain? It underlines this bit and says, no, that's not okay. And why does it say that? It's because it's potentially out of bounds. So overflow assigned to integer overflow in C has undefined behavior, and the SMT type checking fails and gives us a counter model saying, hey, look right here. If your integer is at the maximum number, the addition will be out of bounds and you get an error. And you can see here what I mean by the good error messages being a bit aspirational, because you can see that there's something useful in this counter model, but we're sort of still presenting a whole bunch of like internal compiler state. So we're sort of in progress towards the ability to step through every line of your program and have the type checker tell you sort of what the state of the program looks like at each program point. We can sort of do that now, but it's not pretty to read. Okay, so that all looks good, but there's a couple of difficulties in this endeavor. And the first difficulty is the C programming language. And so you can see that C has all kinds of weird things. It has like weird scoping rules, weird control structures. Like here, you can jump right into the middle of a loop. You can do weird things to variables, like take the address of them and store them into other variables. And all kinds of like weird coercions and undefined behavior and unspecified behavior everywhere. And so if you tried to write a type system for C directly, that would be incredibly painful, and it probably wouldn't even work. So what do we do about this? And the answer is we turn to some work that's already been done. So Kevin, Memarian, Peter Sewell, and a number of collaborators have spent several years developing a system called Cerberus. And what Cerberus is a tested formal semantics for C. So there's a operational semantics for C that's tested against all the known test suites and like was written by reading the standard. And what Cerberus does is it takes your C program and compiles it into a first order functional language. And they use this to build tooling like spec-respecting interpreters for C, but what we can do is we can use this first-order functional language, and because it has like sensible scoping and things like this, we can give it a type system, a refinement type system. And because core also makes all these things like undefined behavior and coercions explicit, we can do things like say, okay, if our refinement type system doesn't prove that every undefined behavior is dead, then we have to reject the program. And so basically what we do is we take C code with our annotations and feed them into Cerberus, which has been extended to handle our annotations, and produce core plus our refinements, our type refinements, which we then type check. And the cyanide type system actually looks, perfectly normal. There's nothing really scary about it. I mean, like there's lots of rules because we're doing lots of fancy things, but none of the rules are particularly surprising. So the basic typing judgment says, okay, I'm going to have some contexts that have like the core computational variables, the logical variables we use in the constraints, and the actual constraints that need to hold for this program to type check. And then we say a term has like some rich type. So this B is like a base type, and the P is the predicate that it satisfies. So we can type check a term T against something like, this is an integer between 0 and 17. And so this is nice and well behaved, and we have we've written it all down, and we have like a type safety proof for it. So we're quite confident in the core type system itself. However, the most of the difficulties lie in the things that you need to do in order to deal with like the sort of actual programs that you run into. And so I said before that like our design goal is to have like predictable, reliable behavior, and this is a human level thing, but we can operationalize it using like some technical properties. So like because we want predictability, we're going to look to prove termination of our type checker. And because we have all this fancy constraint solving, we have to make sure that the constraint solving lies in the decidable fragment of SMT. And the nicest decidable fragment of SMT is the quantifier free fragment. And so we started off by saying, let's make it sure every constraint is quantifier free. But what is an array? An array is fundamentally a mapping from array indexes to its values. And so if you ask an apparently quantifier-free question, like is A equal to B, you can say, okay, that looks good, no quantifiers in sight, but then you think, wait, A and B are functions, and function extensionality is true. So asking is A equal to B is equivalent to asking for all indices, is A of I equal to B of I? And now we've got like a quantifier, and this is like unpleasant. And unfortunately, arrays are everywhere in C. So in this clear page function, we have a whole bunch of loop invariants talking about arrays, and we have to reason about these arrays, and we have to reason about these functions. So this is really like the big technical problem that we've been beating our heads on for a while. And this ties into the other major technical challenge that type inference gives us. So we said, that it's a substructural type system. And if you write down what the type of dereferencing a pointer looks like in a substructural type system, it looks something like this. It says, if you give me a pointer and a linear proof that you own the memory that pointer points to, I'll give you a value back plus I'll return the ownership to you. But when you write a dereference in C, you just write *L. You don't put any resources in it anywhere. That's crazy talk. And so that means that our type system has to infer all of these uses. And this resource usage also interacts with arrays. So for instance, here's this swap function that takes an array of objects and then swaps I and j. And so what do? We take A of I, store it temporarily in temp, put A of j in A of I, and then put temp back into A of j. So it's like, super simple. You could ask it to a first-year student, and like 95% of them would get it right. But notice that something interesting is happening with ownership. So if the objects are like own memory, then when you store it into the temporary variable, ownership is moved out of the array and into the local variable, and then later on it's put back in. And in order to correctly conclude that you still have a contiguous array at the end of the routine, you have to have arrays with partial ownership in them, and you have to do arithmetic reasoning to make sure that everything taken out had something put back in the same spot. And so now we have to do like array reasoning intertwined with the resource reasoning. And so this looks kind of challenging because the fully automatic thing is like fully undecidable, and we could take the Popple move and say, well, we'll just put in enough annotations. And unfortunately, this is too verbose because if you try it, you get large terms to say you can write star L, and because we want like sort of mortal humans to actually use the type system to write an actual program, that's too verbose. And so what do we do? What have we been doing? So we've been turning to an entirely different community of literature. We've been looking at the work on automated verification to see, what do people in at CAV do when they have to deal with arrays. And this has been really interesting because there's been a certain kind of culture clash or mindset shift. So verification says, okay, you use clever math, but then you add heuristics because you really need to succeed as often as possible. And okay, sometimes you'll spin. And for this particular project, we have to say, well, we want your clever ideas, but we don't want your heuristics because we aren't allowed to spin sometimes. And so this means we have to understand what they're doing and then like sort of readapt it to a new setting, and that's been quite exciting. And so now I can wrap up this whirlwind tour and just say that bringing together type theory and automated verification, well, it looks surprisingly plausible, and we may well be able to have a fancy type system that's actually like habitable to use. And there's lots more to the whole pKVM verification project, and you can ask me about that later. Thank you.
Yeah. Thank you for the talk.
Just a sec. We lost slides there toward the end.
Oh, yeah. It seems that we can also not see the room anymore.
Yeah, we can hear you.
Okay. Good. Yeah.
How far into the slides did you get?
Are there any questions from the live audience?
I don't. Oh, yes, I do.
So if there's any questions online, please put them in the Q&A tab. Or you can just click the raise hand button and then you will be invited on stage. You can ask the question live.
Hi, Neil. Thank you for a great talk. I was wondering, in the goal of having usable error messages, does the fact that you're reasoning about the functional language and therefore have to convert back to the actual C code for explaining what's gone wrong, is it a purely invertible transform, or do you run into problems with trying to work out what the correspondence in the functional language is?
So you are right that that's an enormous amount of work. Luckily, this is work that like Kevin Mamarian, who's the main developer of servers, he's already done this work. So it's his PhD thesis, and like many PhD students, he put way more effort into the tool than he really needed to graduate. And so like lots of information is propagated all the way right down. So he has like an interpreter for C, and when you hit an undefined behavior, it'll say on such and such a line you did like exactly this mistake. So in principle, it's a giant problem, but luckily somebody else has solved it for us mostly.
I see there's one online question here. I think I'm going to make that the last question because we should move on to the discussions then. So the question is from Sebastian Graf, and he's asking, how much easier would your job be if the object language's type system already tracked ownership, like in Rust?
The short answer is we don't know. And the reason we don't know is that in Rust, ownership is tied to specific objects, and and the context we're developing cyanide in is like a very low level system. So it's normal there to say, okay, in my data segment, I'm going to allocate some big range of memory, and I'm going to build like an allocator out of it. And you need to be able to track that, okay, I have taken a particular range of bytes out of an object and created a new object out of it. And so you have to remember that the old object has had some stuff taken out, and you need to remember that the new one can be put back there. And the kind of the whole object technique of Rust, it doesn't work well for that kind of thing. So you need to do some sort of additions to it. On the other hand, it's possible that like if there's ownership everywhere, they might write programs in a more verification-friendly style to start with. We don't know, and because we're focusing on verifying a specific program, we can't actually ask the kernel developers to switch their hypervisor implementation to Rust, because it's an example of that's too big a tool chain change to really ask them.
Okay, yeah. Thank you. I think we have to stop here, but let's applaud the speaker again.